This unit is about solutions. Solutions are a homogeneous mixture at the molecular level of two or more substances in a single phase. And the first thing I'd like you to note by this little table of things, solution does not necessarily mean it's a liquid. We can have gas solutions, we can have liquid solutions, and we can have solid solutions. All of your alloys, like brass, which is a mixture of zinc and copper, are solutions. And note, this is not a chemical change. This is a physical change in the sense of it's a mixture of the zinc and the copper. It's not such that they've come together to form a different compound. Likewise, a mixture in the air of oxygen and nitrogen doesn't mean that they have formed some other compound. There's still oxygen gas and nitrogen gas in the air, but it's a homogeneous, so it's the same throughout the entire air at the molecular level. Now, one of the things you're going to note about this unit, very different from some of the other units, is there's a lot of vocabulary and a lot of it seems very similar in its words. For example, for solution, we also have solute and solvent. These are the two parts of a solution. Every one of these starts with SOL. The solute is the part that is getting dissolved. The solvent is the part that is doing the dissolving. We can usually tell the difference between these based on their amounts. The solute is usually the smaller amount. The solvent is usually the bigger amount. So for example, with our first example, gas, our air is about 80% nitrogen, N2. So that would be the solvent. Oxygen is closer to 19%. So that would be a solute. Of course, there are other gases in our air, carbon dioxide and methane and all sorts of things. In much more minute amounts, they would all be solutes. You can have more than just one in the solvent of air. Likewise, an example of a liquid solution, soda, Coca-Cola. The solvent's the water. That's most of the material in the can. And then the CO2, the gas bubbles that are inside that have been dissolved in the water to give it that sharp taste, the fizziness of it. We can dissolve salt in water. Of course, seawater has a lot of different salts, not just table salts. And if you've ever gone to the dentist, it's possible that you had an amalgam for a filling. There used to be mercury and silver for amalgams. Again, solute, what gets dissolved. Solvent, what does the dissolving. In our table here, the G's stand for gas, the L's stand for liquid, the S for solid. And we can have solid solutions, gas solutions, and liquid solutions. You don't necessarily have to worry about copying down everything in that table. It's just examples of the various kinds. But do expect that all three of those terms could be their own questions on a quiz or a test. Now, miscibility is the property of liquids to mix in all proportions to form a homogeneous solution. Water and ethanol, basically water and all alcohols, are miscible since they mix in all proportions. On the other hand, if it doesn't do so, we call it immiscible. They do not form a solution and mixed in all proportions. Diethyl ether is fairly soluble in water. However, the two solvents are not miscible since they are not soluble in all proportions. Honestly, the best example for things that are immiscible, oil and water. What you have in the picture there is diesel oil, a thin film of it on top of water, and you get that little rainbow effect, such as light going through a prism, divides the light into the rainbow of colors. If you look at the oil from a slightly different angle, you can see the color pattern change. That is due to thin film optical interference. Another good example of things that are miscible would be oil and vinegar. In that case, you have to shake it up really well to get it to be kind of mixed together. If not, it would be in layers. So anything that tends to form layers would be miscible. If it would stay all mixed up, it's much more so a miscible solution. As I said, lots of vocabulary for this unit. As I said, lots of terms that are very similar to each other. So here we have saturated, unsaturated, and supersaturated. Basically, these all refer to how much has been dissolved. When something is saturated, we say it contains the maximum amount of solute that will dissolve in a given solvent at a specific temperature. Unsaturated, well, we can still dissolve some. It contains less solute than the solvent has the capacity to dissolve. So in other words, saturated means we've dissolved as much as we can. Unsaturated means we could still dissolve some more. And supersaturated contains more solute than is present in a saturated solution at a specific temperature. In other words, we've been able to actually dissolve more than should be the maximum at that given temperature. Now, we can tell the difference from these three solutions based on what happens when we add a little bit more. If we have a saturated solution and we add it to a solution that in the picture here would just be this clear solution, if we added a little bit more and it was saturated, basically nothing would seem to happen. The solute might float around on top, it might sink to the bottom, but nothing seems to happen. If it was unsaturated, the solute would disappear, it would dissolve, it would be like it wasn't there anymore. However, if it was super saturated, suddenly a whole bunch of crystals would recrystallize, form out of thin air, essentially, and that's what you see in the picture here. We started with this clear liquid, we added a little bit more sodium acetate to it, and suddenly we've got a whole bunch of crystals in the solution. They have all come out of solution and recrystallized. It was super saturated. We tipped the balance and it all started coming back out. So again, we can kind of tell through experiment, saturated, nothing seems to happen. Unsaturated, the solute disappears. Super saturated, suddenly we got a whole bunch there in the beaker that we didn't have before. And that's what you see in the picture is a super saturated solution. Three different things going on depending on the circumstance. And of course, please note they all say at a specific temperature. As you'll see later on, if we were to raise the temperature, we can dissolve more. A little bit more familiar example of saturated, unsaturated goes with fats. Maybe you've heard of saturated and unsaturated fats. Basically, saturated fats are molecules that have nothing but single bonds between all the carbons. And they are called saturated because they are bonded to as many hydrogens as are possible. On the other hand, unsaturated fats have at least one double bond. And as a result, they do not have as many hydrogens because you have to basically substitute a couple of the electrons for the double bond instead of being connected to another hydrogen. And so an example of having saturated and unsaturated fats. Generally speaking, we tend to avoid the saturated fats, and the unsaturated ones are required. You don't need to worry about copying down everything that's listed here. It's just an example to show you the meaning behind saturated and unsaturated terms. Now, there are basically two ways to create supersaturated solutions. The first is to heat the solvent. Remember, the solvent is the thing that does the dissolving. You heat it up, and that allows you to dissolve more of the solute, and then you cool it down very slowly, and that way the solute doesn't recrystallize. You can also evaporate some of the solvent carefully so that the solute does not solidify and come out of solution. So those are the two ways to create a supersaturated solution. The picture here is one of those little hot packs, something, for instance, that you might have in your pocket. You crunch on it, warms up your hands. Generally speaking, they're unstable. They don't last very long, but they do allow you to heat up your hands and your pocket. Just an example of something that's super saturated. And again, the typical process is you heat it up so that you can dissolve more, and then you cool it down very slowly. Now, generally speaking, how do we know what dissolves in what? And what it comes down to is like dissolves in like. Well, like what? Basically, these break down into two groups, the polar substances and the non-polar substances. Again, you may think back to when we were doing our bonding unit, the polar substances like water, things that do not share the valence electrons equally. The oxygen pulls on the valence electrons more strongly than the hydrogens do. And even though a water molecule is neutral overall, that unequal sharing creates this effect where one side of the molecule is a little bit positive, the other side of the molecule is a little bit negative. Little dipole, we call it, acts like a magnet with its positive end and its negative end to connect to other molecules. If you think about a water molecule with its bent shape, hydrogen, water, and then another hydrogen, not straight across, not symmetrical, those are the polar solutes. On the other hand, non-polar, very symmetrical in shape. CCl4 is an example. We have one carbon in the middle and then 4 chlorines going around it, very symmetrical. You can rotate it. Basically, it looks identical to what it looked like before. You can split it in half in a number of different ways. And the left and right side, the top and the bottom, all look the same. Those are non-polar. Well, the polar things tend to dissolve the polar things, and the non-polar things tend to dissolve the non-polar things. That's what we mean by like dissolves like. So alcohols, which are basically, we took away a hydrogen and put on an OH on one of the bonds, not symmetrical, polar. Alcohols dissolve in water. On the other hand, the non-polar, the oils, the hydrocarbons, symmetrically shaped, tend to dissolve other symmetrically shaped substances. Ionic compounds are more soluble in the polar because, of course, the ion, being that it can split into positive ions and negative ions, where you have water, which is already a little bit positive, a little bit negative on its two ends, can be what dissolves them. So ionic compounds are more soluble in the polar solvents than they would be in the non-polar. And what you can see up here in our little table is just an example of how the longer and longer these alcohol chains become, yes, they're not entirely symmetrical with this one OH here at the end, but the longer and longer that chain becomes, the less soluble it is in water. The little infinity sign means that it was totally soluble, whereas in the hexane, which is a very symmetrical hydrocarbon, 6 carbons surrounded by 14 hydrogens, the one that was very polar didn't dissolve very well, but the ones that got longer and longer chains tended to dissolve. So like dissolves in like. Polar dissolves polar. Non-polar dissolves non-polar. Here is another example. Glucose, sugar. We have the sugar over here, and basically the sugar has some of these OH bonds as opposed to just hydrogens, whereas here the hexane has nothing but hydrogens connected to the carbons instead of some of these OH hydroxide linkages. Well, glucose, very soluble in water, while the cyclohexane is not. So here we would have something with this not symmetrical polar aspect, dissolvable in the water, whereas the hexane is not. Again, easy example, oil and water don't mix. Sugar and water, no problem. Okay, we will spend a lot more time with this particular slide later on, but as I mentioned earlier, when we had saturated and unsaturated, they all said at a specific temperature. Well, these are showing you how solubility can change with temperature. And basically what we have for our first picture here on the left is these different salts, how much can be dissolved at a given temperature. And for most of them, note that the curves are going up as we increase the temperature. So more can be dissolved at a higher temperature That's the general rule for solid solutes in liquids. Increase the temperature, we can dissolve more. Now, at the bottom here, we have temperature. On the side, we have how many grams can be dissolved per 100 grams of water. You need to think of this as sort of a proportion. So, for example, for this KClO3, potassium chlorate, at 30 degrees, I can dissolve 10 grams in 100 grams of water. So if I had 200 grams of water, then I could dissolve twice as much, 20 grams. In 500 grams of water, I could dissolve 5 times as much. So it's not only dependent on the temperature, but of course, how much water I was trying to dissolve it in. These are all set to be per 100 grams of water. Whereas, for example, at my 30 degrees of temperature, NaCl looks like about 35 grams of salt could be dissolved in every 100 grams of water. In 200 grams, I would dissolve 70 grams. Now, the opposite is true of gases, and that's what our chart here at the left, or excuse me, at the right is showing. As temperature increases, notice that these different gases, we have methane, oxygen, and carbon monoxide, they're all decreasing as temperature is raised. And if you think about it, again, in soda, when we keep them cold, they tend to be more bubbly. There's more carbon dioxide in the solution. Nothing worse than a hot soda because a lot of the carbonation has escaped. It gets flat. Flat soda is awful. Same is true, by the way, for lakes. More O2 is dissolved in the cool lakes than in the warm lakes. So gases can contain or be more dissolved in the cool liquids than in the warm liquids. Now, later on, we'll spend some time with this chart in which we'll literally figure out how much is dissolved at a certain temperature, how much more can dissolve if we raise the temperature, how much would come out of solution if we lowered the temperature. So we'll actually be reading this chart later on. Now, when it comes to pressure changes, for liquids and solids, pressure changes don't really do much for solubility. However, if we're talking about how much gas is being dissolved, the amount of pressure, air pressure that's related to the solution is a factor. Again, you can think of this as being something that, you know, if you have bubbly water or soda, the moment you open it up, you can hear the pressure being released. Well, and then suddenly there's a lot of bubbles that are rising to the top of the solution because now the pressure above the solution is less, and so gas can come out. And that's what you have in your picture here. We have a, relatively speaking, large volume of gas above the solution, lower pressure. Remember, those are inversely related. Increase the volume, you lower the pressure, and so we don't have as much gas molecules in the solution. On the other hand, in the lower picture, we have decreased the volume, increased the pressure, and so we now end up with more molecules that have been dissolved, more gas molecules that have been dissolved in the solution. There is an equation to account for that, where C is the concentration in molarity of the dissolved gas, K is a constant that would depend on the particular solution, and P is the amount of pressure. We won't be doing any math related to this equation, just would like you to see that there is an equation that relates the level of the pressure to the concentration. There are 3 main factors that would affect how fast something would dissolve: the rate of the dissolving. We can increase the surface area, break it into smaller particles. We can stir it up, and we can increase the temperature. All of these would increase how fast the material would dissolve. Basically, when we stir something, we make the material come in contact with the solvent more quickly. When we increase the temperature, the motion of the particles speeds up, moves about more quickly. And if we increase the surface area, it can get to more material more quickly by breaking it up. When it's a big piece, the center is not directly in contact with the solvent, and so it doesn't dissolve yet. But when we break it up, the middle gets exposed much more quickly, and so will dissolve more quickly. So 3 factors that can affect the rate of dissolving. And of course, a big piece at a lower temperature would not dissolve as quickly as little pieces at a higher temperature. Okay, some more vocabulary. Electrolytes versus non-electrolytes. An aqueous solution, that's a water solution that's had something dissolved in it. Acids, bases, and salts dissolved in water are electrolytes. Basically, electrolytes form ions in solution. If it's a salt, they fall apart into their cations and anions. They break apart. We call that dissociate. With acids, they create a lot of hydrogen ions in solution. Bases can create a lot of hydroxide ions, OH minus ions in solution. Non-electrolytes, on the other hand, don't dissociate in solution, so they don't break apart into ions. They are typically polar covalent substances, such as sugars. They may dissolve, but they don't break apart in ions when they dissolve. And so, as an example here in our picture, the one on the left has sugar molecules been dissolved in the water, don't break apart into ions, do not conduct electricity, little light does not light up, there is not a current that is going through the solution. On the other hand, get a few ions, a salt maybe that breaks apart into 2 different ions, we get a little weak light, dimly lit. Different kind of salt, or maybe a really strong acid, lots and lots of ions, bright light. You may have heard the term electrolyte in a sports drink. Some salt in there becomes electrolytes, dissolves in the solution, and replenishes the salts that maybe you're using up in terms of exercise. But another experiment that you can run to test whether it's an electrolyte or non-electrolyte, does the light light up? Now, there is some math in this unit, not as much as in the last, but for the most part, we will want to know what is the concentration of the solution. In other words, how much actually got dissolved. We will do principally the first one and the last one here, mostly the first one, which is molarity. The molarity, using a capital M, is the number of moles of solute per liter of solution. Please note, the solution is made of both the solute and the solvent. This is moles per liter. We can also have molality, which is moles of solute per kilogram of solvent. So that's a little bit different than the one above it. We can have the mole fraction, which is moles of one part of the solution divided by the total moles of the solution. And then we can have the mass percent. Now, in this case, the mass percent is done in terms of grams per grams, but we can also have a percentage in which it's grams per milliliter of solution. That's a very common one. And the key here is it's done as a percent, though sometimes we see it as parts per thousand or even parts per million, in which we may have the solute, not very much of it has been dissolved in the total solution. Parts per thousand might only be a few parts in, say, 1,000 milliliters that's been dissolved. Parts per million, ppm, hardly any has been dissolved. You often see ppt and ppm when we're worried, for instance, in contaminants, maybe something we don't want in our drinking water, for example. Even at parts per million, we may be worried that too much of it would be not healthy for us over long periods of time. So 4 ways at looking at concentration. We're going to spend most of our time on the first one and then a little bit of time on the last one. Not going to be doing very much of the middle 2 at all. So let's look at example of the first one. This is doing molarity. So 0.435 grams of KMnO4, potassium manganate, is dissolved in enough water to give 250 milliliters of solution. What is the molarity? Again, molarity is moles per liter. So I got to take the grams and turn it into moles. We do have to do some mole problems here. 0.435 grams divided by the 158 grams of KMnO4 gives us 0.00275 moles of KMnO4. Now, where did the 158 come from? That is the molar mass of KMnO4, the potassium, manganese, and 4 oxygens add up to 158. Do that off the periodic table. We also have to change the 250 milliliters into liters. So we divide by 1,000. Now, once we have the grams into moles and the milliliters into liters, we take moles divided by liters and we get our molarity. And note our molarity is done with a capital M. So this would be a molarity problem. I say it's the forward direction where we started with the grams and then we have figured out the molarity. You will also have to do this problem in the backwards direction, in which the question might be how many grams are needed to produce a certain molarity. We'll look at that next. But again, molarity is moles per liter. So we had to change the grams into moles by dividing. If it's not already given to us in liters, we have to change the milliliters into liters, again by dividing by 1,000. And then once we have moles and liters, it's a division problem to turn it into molarity. We are solving for the concentration, how much has been dissolved in the solution. Here we're going to go in the opposite direction. We want to find out what mass, how many grams were needed to be dissolved to make a certain concentration, a certain capital M molarity concentration. So we want to know what mass was needed to make 250 milliliters of a 0.05 molar solution. Notice that I've taken my molarity formula and rearranged it to solve for moles. M being molarity equals moles over liters, the volume in liters. I've rearranged that to moles equals M times V, capital M for molarity, V for the volume. So again, we need to make sure that our milliliters is in liters. So we had to divide by 1,000. Then we could take our 0.05 M, that's the M part, times the liters, and that gives us our moles. We do that multiplying to get our moles, and then we take our moles times the molar mass to get our grams. Where did the 90 come from? The 90 comes from adding up 2 hydrogens, that's 2, plus 2 carbons, that'd be another 24, plus 4 oxygens, that would be 64. Adding all of that up together gives us 90, and then times the moles that we got from our molarity formula gives us 1.13 grams. So it would take 1.13 grams of the oxalic acid in 250 milliliters to give us our 0.05 molar solution. So this would be an example of going backwards. The previous example, if I go back, that was an example of what I say going forward. We knew the grams, wanted to calculate the molarity. Here, we know the molarity, we want to figure out what grams was needed to get there. So these are the kinds of math problems that we'll be doing, I'd say 70, 80, 90% of the time. And the percentage ones, the percent concentrations will be the rest of our calculations for our solutions. So here are some quick examples of the other types. And again, the bottom one is the one we'll be doing the most. And again, these are just examples. We want to dissolve 31 grams of ethylene glycol in 250 grams of water. Here, I already have the moles for you, 0.5 moles. So these are examples. Molality, moles per kilogram. Note I have 0.25 kilograms here for the 250 grams of water. So divide 50 by 1,000 gives us kilograms. So 0.5 divided by 0.25, 2 lowercase m for molality. Our mole fraction, 0.5 moles divided by 0.5 moles plus 13. Where'd the 13.9 come from? That's the 250 grams divided by 18 for water, 18, 2 hydrogen, 16 for the oxygen. So 250 divided by 18 gives us our 13.9 moles. The reason for the adding is it has to be the total number of moles in the solution. So 0.5 divided by 14.4 gives us 3.5%. And then here, our mass percent, 31 grams of the ethylene glycol divided by the total grams. In this case, times 100 gives us our 11%. And then later on, we'll look at grams per milliliter or even grams per liter for other percentages of concentration. So some other examples of calculating concentrations, but we'll do molarity the most, moles per liter of solution. Okay, some more vocabulary to think about. Colligative properties. Colligative properties are where when we add a little bit of solute to the solvent, it actually changes the property of the solvent. Some of the properties that we look at are things like boiling point, freezing point, melting point, and vapor pressure, also osmosis or osmotic pressure. Again, colligative properties are things in which the property changes when we add something to it. A everyday example that you might have seen on TV, even in the recent past, is adding salt to a road so that they don't ice up as quickly. By adding the salt, it lowers the freezing point, and so the streets don't ice over as easily. The reason I said you might see it on TV is they've had a lot of snowy weather back east, freezing, and with our recent rain here, some snow up in the mountains, and so to prevent them from icing up quite as easily, they add some salt to the streets. These depend on the number of solute particles relative to solvent particles and not on the kind of solute particles, but they can change the freezing point, melting point, boiling point, etc. Basically, this is just an example of vapor pressure that can be changed. In the top diagram, we have just solvent by itself, and so there's a certain amount of vapor pressure above it. We add some solute to that, and notice that the vapor pressure is now lower in the gas above the solution. There is some math related to colligative properties. We can actually calculate what is the change in temperature. In this case, the little triangles stand for, it's called delta. It stands for change in. So the change in temperature, the B for boiling point, the F for freezing point. Notice that these depend on the molality. That is the moles per kilogram of concentration. The K is a constant that depends on the material that we're talking about. So we can look at the change in the boiling point or freezing point, and it's proportional to the molality. So what you have here is basically a diagram of solids, liquids, and gases going from solid to liquid or liquid to gas for boiling or freezing. And basically what we have is this line right here where it would be pure solvent. And then what happens is we add some solute to it, we dissolve something into it, and literally it changes the line. And so now we have a higher boiling point or a lower freezing point for that particular substance. And we can do that calculation. Here is an example of the calculation. Don't worry about copying it down. Freezing point depression. What is the freezing point of a solution containing 478 grams of ethylene glycol antifreeze and 3,202 grams of water? So, just like in a previous problem for molarity, we need to make moles. So we take the 478, we divide it by the 62 to turn that top part into moles. The bottom part has to be in kilograms. So note it's 3.2 kilograms. The 3,202 was divided by 1,000 to make it kilograms. Moles per kilograms gives us the molality. The 1.86 is a constant for water. Multiply the two together, we get 4.48 degrees Celsius. In other words, we have lowered the freezing point of this material by almost 4.5 degrees Celsius. That would be about 9 degrees Fahrenheit. That's what antifreeze does. It prevents your radiator from freezing up in cold weather. Likewise, the antifreeze will keep your radiator from boiling over if it gets too hot. And so you have an example of the math for a colligative property. And osmosis is where you go from higher concentrations to lower concentrations for a solution, very similar to the way gases went from with diffusion from higher to lower concentrations. Osmotic pressure keeps it from doing so.